Thank you very much, David, for the invitation to speak here. So I'll talk about some recent work which I did, which in a sense is still work in progress. So I'll start with some motivation of what my ultimate goal is. Well, I mean, the most ultimate goal is to construct as much examples of locally compact quantum groups as possible. A locally compact quantum group, I'll give the definition later, is meant in the sense of custom-Monson glass. And in particular, I want to construct quantizations of non-compact semisimple Lie groups. But actually for today, I will focus on a class of quantizations of solvable Lie groups. More precisely, of Borel subgroups of complex semisimple Lie groups. So I'll start with the data of a semisimple complex algebra. G, and I suppose that I have fixed inside some Borel Lie subalgebra B. And then it's well known that these things admit quantizations, so their universal enveloping algebras can be deformed with a parameter q, which in my talk will be a concrete number, and specifically it will be between 0 and 1, because later on I will want to use also star structures, and then it will be important that this is a real number. So you can construct a family of Hopf algebras UQB living inside UQG. And so these UQGs, they're deformations of the universal enveloping algebra of G. And they can be seen as generated by very specific generators. So you have some generators which in my conventions I will label by the weight lattice of my Lie group, of my Lie algebra. I have some generators which are labeled by the simple roots, which I chose associated to my Borel subalgebra. And then I also have some elements associated to the negatives of the simple roots. So UQG will be generated by these, and then UQB will actually be a subalgebra generated by these, but also they will just be given by the universal algebra generated by the by the relation satisfied by k omega and ER. So just to give you a sample, I won't write down all the defining relations. But for example, we have that the commutation between the k omega and the ER is very simple. This is just a kind of Q commutation. So we take Q to a certain power, and then we take the natural pairing between the weight omega and the simple root alpha r. We take Q to this power, and then this is used to exchange the k omega and the ER. And then you have some more complicated non-quadratic relations linking the different ERs, and these are called the Q-stated relations. Okay, so these two things completely determine my subalgebra UQB. And for UQG, I add this extra family of generators FR. And again, you have to specify all the commutation relations, but I'll only focus on one of the commutation relations, namely between the ER and the FS. These are given by the following. So if S is not equal to R, they just commute, but if R is equal to S, then I have the following interchange relation, where QR is given by a certain power of Q. Okay. So actually there's a, careful. There's a more conceptual way of defining the UQG starting from UQB. So So to get UQG from UQB. So first you notice that there's a skew pairing. In the sense of Hopf algebras between, on the one hand, UQB, which has these generators ER and K omega, and a copy of UQB, but with the opposite multiplication or opposite co-multiplication, which you can see as a quantization of the opposite Borel algebra UQB minus. And so this I will see as being generated by the FR, and then just a copy of the K omegas, which now I will write as L omegas. Okay, so the relations here are very similar to the ones here. And the point is that from general theory, if you have two Hopf algebras with a pairing, there's a certain Hopf algebra you can create from it called the Drinfeld double. So we have a Drinfeld double which I'll write U tilde Q G. And so this is going to be generated by just a copy of UQB and UQB minus with very specific interchange relations between the two sets of generators. And in particular, the identity which I wrote here will be true also for this Drinfeld double, except that one of the k's will be changed by an L. So we have here the S, K alpha R minus L alpha R inverse. And another thing is that K omega, L omega inverse is actually a central element. Okay. So this implies, and it will be group-like. So I should say that, of course, I told you these were Hopf algebras, but I will not write down the specific co-multiplication because it will not be really important for the talk, but the co-multiplication is really easy to write down. So this is, this will not be too important. But I just mentioned here that this element will be central in the Drinfeld double, and it will be group-like. So this actually means that I can take a quotient Hopf algebra by putting K omega equal to L omega, and this will precisely be the UQG that I gave here. Okay, so just starting from UQB in a very general construction, I can construct UQG. But actually for my talk, it will be discover, which I will need. Now, not only do I have the Drinfeld double, which is a Hopf algebra, so let me write this. So this is a Hopf algebra. But there's also another kind of algebra that I can define, which is called the Heisenberg algebra, or Heisenberg double. So this I will write as HQ of B. And again, I'll not write all the commutation relations, but just to give you a sample, the interchange relation in this algebra will now be changed in the following. So actually one of the copies of K will disappear, and I just get the minus L alpha R inverse, which is left. On the other hand, my K omega and L omega will no longer commute. So K omega L chi, say, this will be equal to Q to the minus omega chi L chi K omega. So I get a specific copy of the quantum torus inside this Heisenberg algebra. And the point is that this Heisenberg double can be used to link my Drinfeld double with something very easy, namely just the tensor product of UQB and UQB minus. So we have what is called the Bigalow object. So this means that my HQB has first of all, it has a right coaction by my twin field W tilde QG. On the other hand, it also has a left coaction gamma by the tensor product of UQB with UQB minus. And I will not give here the definition of what precisely constitutes a bi-Galois object. So it has to satisfy very particular conditions. But for example, one of the conditions would be that alpha and gamma commute. So if I first do the alpha and then I apply on the HQB here the gamma, it's the same as doing it the other way around. Okay? And this theory of bi-Galois objects for Hopf algebras this was developed by Peter Schauenberg in a couple of papers actually. And the point which I want to make here is or well, maybe I'll come back to that later. So actually, what I want to say is that a very specific class of such Galois objects or bi-Galois objects can be constructed from two cocycles. In particular, here it's related to the R matrix, to the universal R matrix. But for my purposes, it will be important not to use the specific two-cocycle interpretation, but to use this Galois object interpretation because it will be much more amenable to operator algebraic purposes. So this is actually what I want to have as a goal. So the goal is to interpret the structure on the level of operator algebras, and more specifically in the setting of the locally compact quantum groups. So as said, I'll recall the definition of locally compact quantum group in a moment. Now, the first thing which you need to have, if I actually want to define things on the level of operator algebras, is that I need star algebras. I don't just need algebras, I need to have a star structure around. So we will use the following real structure. So we basically have two copies which commute in a certain way, and the star is just going to send this copy to this copy in a very particular way. So the ER is sent to FR L alpha R, and the A omega is sent to L omega. And you can check that this star operation it's compatible with the commutation relation, so it doesn't actually reduce. Well, it's well defined on the algebra, and it means that we get star algebras. And now I'll use new notation. So this guy here with that particular star structure, I'll write UQ BR. So this is basically just the tensor product of UQB and UQB minus, but with that particular star structure. And the idea is that BR, you can just see it as as B. So B is a complex Lie algebra, but I just interpret it as a real Lie algebra, and then I complexify it again. So basically, this BR you should see as B times C. Okay. Then I have my Heisenberg algebra HQB. So with this specific star structure, I'll write this as HQRB. And then the U tilde QG, I'll now write as U tilde Q K, where K is the compact form. So the point is that I mean, ultimately, this guy here will be easy to construct. So U tilde QK is easy to integrate because this will be basically up to an amplification by some toric part up to amplification. This will be a discrete quantum group. And then basically the whole theory is algebraic, and there's no real problems with the operator algebraic structure. The second guy we want to integrate is the HQ. So this we will do by, so this can be integrated by linking it to the dual quantum group of U tilde Q K. So this is the main observation, which is not completely obvious from general theory, how you can link this algebra defined by generators and relations with the dual of the U tilde QK. So that I'll explain at the end. But once we have this guy with its coaction by U tilde QK well defined on the level of operator algebras, in a sense then this guy is automatically integrated by general theory. Of fellow objects, of my fellow objects. Because the point of Schauenberg's theory is in fact that he tells you that if you have a bi-Galois object like this, it's actually completely determined by one of its parts, just by the Galois object, for example, here. If I only have this right coaction, actually I can reconstruct both the Hopf algebra here together with its coaction in an almost unique way. Okay, so just from having a Galois object, I can construct a bi-Galois object, and the same thing holds on the level of operator algebras. So I'll also talk a bit more about that later. But basically, if I know how to integrate this, and I can show that this will give me a Galois object on in the setting of operator algebras, then also this guy will be well defined by a general theorem. The only thing is that the precise description of the operator algebraic version of this, I cannot yet relate completely rigorously with the quantized universal involving algebra itself. Okay, so there's some problems with unbounded operators which I still have to figure out, but morally this one has been integrated by this general theory. The only thing which I have to warn though is that so here I just took the ordinary tensor product, Now for the theorem, I can't actually take the usual tensor product, but I have to twist it a little bit. So the point is that in my tensor product here, I cannot have a commutation of the k omega and the fr, but these will be q commuting also. Okay, so there's a little q commutation going on between the two parts, but what is important is that even though I have this q deformed tensor product, I still have that the ER and the FS will always commute. So that basically the behavior of this, so maybe I should write this then as u tilde, and here also there will be a little extra q commutation. The point is that the commutation here very much resembles the one for u of VR itself. Okay, so it's really a kind of direct q version of the universal enveloping algebra of the reunification of P. So this is just a small technical point. Okay, so now I'll try to get in some more details and give some definitions. So first, I'll try to very briefly describe the notion of locally compact quantum group as I will use it in the rest of this talk. Basically, I'll use this definition due to customers and pass in the setting of Neumann algebras. So, a locally compact quantum group consists of the Neumann algebra M with co-product delta. So this means that I have a normal unital star homomorphism satisfying co-associability, just like for algebras. But the important thing is that I also have invariant weights. So there exist normal semi-finite faithful weights phi and psi, such that I have what is called left invariance and right invariance, where these identities have to be understood as taking x just a positive element in M, and then I have this identity. Okay, so these are the analogues of Haar measures, left and right Haar measure on a locally compact group. So in general, we can interpret M as being either algebra of essentially bounded functions on some locally compact quantum group, or we can also view it as being a generalization of the group von Neumann algebra of the locally compact group. And these two pictures, you can reconcile them by seeing this identity as kind of generalized quantity duality. This is all just formal, it's just for interpretation that you use these different viewpoints. On the other hand, there is a specific duality theory for locally compact quantum groups, so duality theory. So from M delta, you can actually construct a dual locally compact quantum group. And for example, if I would interpret this M as being functions on G, then this duality would let me interpret M hat as being the group von Neumann algebra But I will try not to use this formalism too much, but it's good to keep in mind that you can think of it this way. So I will need a very specific kind of action of this of these locally compact quantum groups, which are called null objects, or also quantum torsors. So null object or quantum torsor is a von Neumann algebra N with a coaction alpha for a given locally compact quantum group M, and I will ask certain properties. So the first property which I ask is that it's integrable, meaning that the natural map going from N to N is semi-finite. Okay, so there's enough positive elements such that if I apply alpha to it and then I integrate out a second leg, it will give me actually again an element, a bounded element in N. Okay, so if I have this integrability condition, then I can formulate a kind of notion of freeness. So if I have an integrable coaction, you can show that, so there's a certain notion of cross product you can take, generalizing the ordinary notion of cross product of a von Neumann algebra with a group action. Okay, so you let M act, the dual of M, you can let act as a translation on N. So this is a well-defined von Neumann algebra, but under the condition of integrability, you can show that this has a natural normal representation on L to N. So I need this integrability to make sense of this map, but the freeness condition actually tells me that this is going to be an embedding. Okay, so this is the second thing that I ask, and it corresponds morally to essential freeness on the level of classical group actions on measurable spaces. And then the third condition is kind of the opposite of freeness, namely is the ergodicity condition, which tells me that if I have an element which is fixed by the coaction, which I can express as saying that alpha of x is equal to x tends to 1, then it implies that actually x is a scalar. Okay. So these two are kind of, if you think about classical actions, and freeness is kind of the antithesis of ergodicity or homogeneity. So this will have some very particular consequences. So freeness together with the ergodicity will actually imply that this is going to be not only embedded here, but will be an isomorphism. So I will have that this cross product is a type 1 factor, more precisely b of L to n. And the second thing is that, well, actually this, so if I write this here, so let me write n alpha as being the set of all x such that this identity holds, then this operation here will be an operator value to 8 from n plus to n alpha plus. So in particular, if I assume that I have my ergodicity, then n alpha plus is just going to be the real, well, here I should maybe put the extended. And this is just going to be the extended positive reals. And so it means that there exists a weight phi alpha and a z weight phi alpha on n, such that phi alpha of x is equal to identity tensor phi alpha of x. And this will allow me to create a very particular unitary G on the level of the standard Hilbert spaces. So basically, with respect to the GNS maps for phi alpha and the left invariant weight for my M, this map is given by the following. So x tends y to alpha y x tends 1. And this is, by these assumptions, this is going to be unitary. And in a sense, this is a very important object in the theory, so it's called with Galois unitary. And so what I mentioned earlier on is that there is a kind of reflection principle for these Galois objects. Theorem. So if an alpha is a Galois object, for a delta, there exists a locally compact quantum group P delta, essentially unique, and a left Galois object structure for P delta on the same von Neumann algebra. And then again, gamma and this alpha are supposed to commute also. Okay, so in particular, this theory allows you to construct in a way new quantum groups by this reflection procedure, which is kind of like a generalization of twisting by two cocycles. So now I want to come to the title of my talk, which was I-factorial quantum torsors. So for this I will relate first these Galois objects, with the notion of projective representation. So projective representations and I-factorial quantum torsors. So projective representation, even if you look at it classically, I mean, what is a projective representation of a locally compact group? You can see it as an action of your group on the type 1 factor. So an action of the group on V of H for some Hilbert space H. So in that sense, the definition of projective representation for a quantum group is straightforward. So we say that a projective representation for locally compact quantum group M delta is simply a right coaction on the type 1 factor. So we just have some V of H with a right coaction of N. And then, I mean, again, if you think classically, you know that projective representations are determined by two cocycle. And so in the setting of locally compact quantum groups, the role of two cocycle will be played by a Galois object in the following sense. So considerations A, if theta projective representation, then we can look at the cross product of BH with M, and we can look at the relative commutance of BH in this cross product. And again, general theory tells you that if you have a cross product by a locally compact quantum group, this actually has again a dual action by the dual quantum group. And it's easy to see that if I take the commutant with the co-invariance, the dual coaction will restrict to this. So if I do it in this specific setting where I have a coaction on B of H, then the restriction of the dual coaction to N will actually give me a Galois object structure on N for the dual of N. And conversely, if N alpha is a Galois object for N delta, then I told you that the cross product of N with M will actually be a type 1 factor, namely B of L to N. So this cross product with the dual coaction by N hat is projective representation. Okay, so there's kind of a duality between Galois objects for a quantum group and the projective representations for its dual, and this can be made precise. So there's a notion of outer equivalence you can make for projective representations, and then the classes of outer equivalence projective representations are actually in one-to-one correspondence with the classes of the Galois objects for the dual. Okay. And the point is that what we can do now. So I told you that their projective representations are dual to Galois objects, but there's nothing saying that you can't have both structures on the same object. So what we'll look at now is projective representations which at the same time are Galois objects. I-factorial quantum torsor is a Galois object structure on some B of H. So it's at the same time Galois object and projective representation. So this was briefly studied in the setting of Hopf algebras, in the setting of finite dimensional Hopf algebras. Here taken by algebra. Yeah, so an example. Given by considering a locally compact quantum group, and you consider just this Heisenberg algebra, which is the cross product of M with itself by the multiplication. So this is going to be a 1-factorial Galois object. 1-factorial Galois object or 1-factorial quantum torsor for the tensor product of M with itself. So as you may recall from the beginning, my motivation concerned a certain Heisenberg algebra in the setting of Hopf algebras, but the point was that there I took the Heisenberg algebra of something which did not yet have a star structure, and then I put the star structure directly on the Heisenberg algebra. Okay. So the point is that somehow you expect your Heisenberg algebra to be a simple algebra, but for the situation I'm interested in, it's not immediately an operator algebra, but somehow you expect it to be of this type. Okay, and if your original star algebra was already a locally compact quantum group, then this works out just fine. Okay, so if I start with something which already is implemented in the operator algebra setting, then indeed the Heisenberg algebra of that will be something of this type. And so the main theorem concerning these 1 factorial quantum torsors is that they have a very nice duality theory. So for this, I have to introduce the following. Note, if n alpha is a Galois object for n delta, we actually have an adjoint coaction of the dual. So we have up alpha from n to n tensor the dual of n just by conjugating with this Galois unitary. So we take x and we send it to g star x tensor 1 g. Then the theorem which I want to state is the following. So if n alpha is a 1 factorial quantum torsor, then also this new adjoint coaction will also be a Galois object. So then also n with the adjoint coaction by the dual. So if this is quantum torsor for n delta, then this is a 1 factorial quantum torsor for the dual. And moreover, applying the operation twice gives me back the original coaction. So the neatness of this construction lies in the fact that I can now combine this duality with the twisting technique that I had told you about earlier. So if I start with 1 factorial quantum torsor n, and I have this, now I will use this notation, so I have a quantum group G acting on n. Well, I told you, then there is on the other side another quantum group acting, making it a bi-Galois object. But by this statement here, I actually also have on n a Galois object structure for the dual of G by looking at the adjoint action. And nothing prevents me from applying again this twisting construction, but now with respect to this dual coaction. So this means that I have here some other quantum group H acting. And now I can just repeat this construction. So for example, for this L, I can also look at its action of its dual by the adjoint, and again apply this twisting technique and get again a new quantum group, let's say T. Okay? And so in principle I can go on indefinitely because there doesn't seem to be any necessary relation between all these different twists that I get. So in principle this would lead to an infinite family of locally compact quantum groups. For example, if I look at the Heisenberg algebra which I had here. So I start with my action of n tensor m hat, and the first step is actually not going to do anything. So if I look at the dual coaction, the adjoint coaction, well, the dual of this is going to be the same locally compact quantum group, and actually the dual action will also be the same. So this will not give me anything new. On the other hand, if I do the twisting technique, twisting a locally tensor product of a locally compact quantum group and its dual across the Heisenberg, this will give me the Drinfeld double in the setting of locally compact quantum groups. And now I get something interesting if I take the dual, because the Drinfeld construction is not self-dual. So on my Heisenberg algebra, I also get I-factorial object structure for the Drinfeld co-double. And now actually I don't even know what I get here. And so I can do the twist of d hat m across the Heisenberg and get something new, but I don't know what it is. I mean, I'm quite sure that it will be isomorphic to something which is known, but I couldn't figure out yet what it is precisely. But I think for this particular example, it won't give you an infinite family, it will probably be something cyclic here. But I don't understand it completely yet.
Wow. What is the Drinfeld codial?
So it's basically, you take the tensor product of m and m hat, and you twist the co-multiplication by putting the multiplicative unitary in the middle. So you have this, and then the delta of the Drinfeld co-double is going to be something like, so this is in the tensor product, and I put something like 2, 3 star, sigma 2, 3, delta tensor delta hat of x. Something like this.
So it's not the Drinfeld double or something?
No, so the Drinfeld double will have the same co-multiplication as on m times m, but,
yeah, but it's not the Drinfeld double or something else?
No, yeah. Because in the Drinfeld double you will change the multiplication, in the Drinfeld co-double you change only the co-multiplication. But yeah. So maybe in the last few minutes, let me come back to the original setting. Application. UQB in the operator algebraic setting. So from the beginning I recall that we had this Drinfeld double for UQB, which was UQ tilde G, and then I considered its compact form in a way. So this was a Hopf star algebra. Which projected surjectively by killing one of the Carton copies onto the usual version of the quantized universal enveloping algebra of K. For K compact semisimple algebra. And the point is that inside the dual of UQK lives Hopf star algebra, which I will write quantized polynomial algebra of the integrated compact Lie group of the Lie algebra K. And because the K is a compact Lie group, it's very easy to consider its integrated version into a locally compact quantum group, even a compact quantum group. So this has completion into locally, but actually a compact quantum group and infinity K. And by results of Lewandowski-Seidelman and also Reshetikhin Yakimov. One can show that this, as a von Neumann algebra, it's actually really easy. It's just a tensor product of a type 1 factor, which very concretely can be realized as bounded operators on some tensor copies of L to n. So so the big N here is just the length of the longest element of the Weil group, and then I just have to add another copy of some of a torus. And the point is that the torus acts on L infinity of k by quantum group automorphisms. So this means that I can take a cross product with this torus action, and that will give me a 1 factorial quantum torus. So if I take an infinity qk cross t, this will give me a 1 factorial quantum torsor for the tensor product of L infinity qk and just the ordinary group algebra of t. So this I can actually identify completely with now all bounded operators on the tensor product of L to n. And, let's say L to t. And the dual of the reflected quantum group LQ infinity k tilde. Okay, so this gives me a quantum torsor for this tensor product, so I can reflect this across this Galois object and get a new quantum group. This one I will write L infinity q tilde k. This will actually be have as its dual something which integrates my u tilde qk. Moreover, so if I write so since this is a 1 factorial quantum torsor, I can look at the adjoint coaction by the dual of this, and the adjoint coaction of the let's say the group von Neumann algebra of this guy, so L tilde q k on n will integrate the action of q tilde k on the Heisenberg. Will integrate the coaction of u tilde q k on this slightly deformed Heisenberg algebra of the Borel type. Okay. So what I mean by this is that there is a very concrete realization of the generators of this Heisenberg algebra as unbounded operators affiliated with my von Neumann algebra n here, in such a way that the coaction, the adjoint coaction on n, will give me precisely the original coaction on my deformed Heisenberg algebra by U to QK. And maybe very briefly, I'll just mention that this identification at the end is what is the most unintuitive, maybe, part of the whole thing, because it requires to relate this Heisenberg algebra with a certain algebra inside this crossed product. And so what happens is that inside this crossed product, I have my algebra Pol QK, and I can take its crossed product just algebraically with this torus. And if in this algebra I invert certain elements and add certain polar decompositions of elements, it turns out that I have an equivariant map from this Heisenberg algebra into this extended version of the amplification of Pol QK. And that is something which is based on earlier work which I did with Sergei in 2015, and which has also independently been observed by Borel and Yakimov, who actually constructed on this deformed, well, they constructed on a certain very closely related Heisenberg algebra quantum cluster algebra structure. And so part of further research which I want to do is to use this quantum cluster algebra structure, which they constructed on this Heisenberg algebra, and relate it with the operator algebraic structure, with the operator algebraic integration here. Okay, and I'll stop there.
Thank you very much. Any questions or comments?
So your main motivation was to construct locally compact quantum groups, starting with deformed duality reactors. Do you have just general locally compact quantum group like this, or some special class?
Well, I don't know what's, so the special class, I mean, it would definitely be a, well, there's certain unimodularity going on, so for
It will be unimodular.
one of the two, like the quantum group where it's dual, one of them will be unimodular, yes, because they're kind of related with the compact one, where it's definitely unimodular. And that's one thing. The other thing is that it would be very interesting for these kinds of examples to look at what happens with if there's any complex structure, because they're kind of composed of a complex part and an well, a homomorphic part and an anti-homomorphic part. But I don't see how that can be exploited on the operator algebra level, so that would also be very interesting to see. I mean, yeah, there's no general theory of what is a complex structure on a locally compact quantum group. So it would be interesting to see in these examples if something can be done with that.
And related question: if you want to construct a locally compact quantum group with prescribed properties, some compactness, discreteness, etc., is it clear which conditions should you impose onto initial algebra?
I mean, if you start from the quantized enveloping ones, then you will only get the compact ones.
Yes.
Starting from the compact algebra.
So is it sufficient? Is it necessary?
I think so. Yeah.
Edwin?
About halfway through, you said that a projective representation is the same as a right fraction on a type 1 factor. Is it possible to explain very quickly how that follows?
Yes. So basically, I mean, if I have just an ordinary group and I have a coaction of it on B of H, then this can be shown to be the same as saying that I have an action of G on B of H. So this is just general, it doesn't matter if it's B of H or not. If this is a classical locally compact quantum group, then it gives me an action on the von Neumann algebra here. But now if this is B of H, then it's well known that any automorphism of B of H, it's inner. right? So alpha of g I can write as at u g for some unitary u, and then because of u g is unique up to a scalar. So this means that since this is an action, the fact that alpha g is equal to alpha g after alpha h will imply that ug UH has to be equal to UGH up to a scalar. And then you can easily see by the associativity of the group that this is going to be a two-cycle. And you have to choose, of course, the section here in such a way that things will be measurable, but you can show that you can do that.
Ulrich?
So with this description, if you think about projective representations, then they also correspond to honest representations of central extensions.
Yes.
Is there anything
No.
analogous?
No, so this description doesn't work in the quantum setting anymore. Not that I know of. So it doesn't seem possible to give a description in terms of central extensions.
Is there an analog of this? I mean, of the omega GH of this co-cycle?
So the analog would be the Galois object.
But is there some cohomology theory that classifies those somehow? Or?
Again, not in general. So I mean, if you look, there is also a notion of two co-cycle, which is more restrictive than the notion of Galois object. And then for those two co-cycles, if you put another restriction on them, which is called lazy two co-cycles, then there's a kind of two cohomology theory you can do. But in general, the point is that if you look at two co-cycles, they won't form a group in any way. They will just form a pointed set, and there's very little cohomology you can do with them.
Any more questions? Comments? Maybe we can talk further over cake and tea. Thank you very much.